Who doesn't like colors? A colorful display of fireworks is always a visual treat. Did you know fireworks mostly contain compounds of D block elements? But why and how are these compounds colored? Let us learn about the secret behind the colors in compounds of D block elements. For a compound to be colored, the metal must have incompletely filled d orbitals. Almost all transition metals have incompletely filled d orbitals. For example, vanadium has an outer electronic configuration of 4s2 3d3. Chromium has 4s1 and 3d5, whereas iron has 4s2 3d6. Let us consider a copper atom as an example. It has an outer electronic configuration of 4s1 3d10. There are no vacant d orbitals in the copper atom. But if copper gets oxidized by losing two of its electrons, one of the d orbital becomes half filled, and therefore all the compounds in which copper exists as Cu2 plus are colored. In the case of zinc, which has an outer configuration of 3d10 4s2, there are no empty d orbitals. Even when it forms Zn2 plus ion, the electrons are lost from the 4s orbital, leaving the filled 3d orbital intact. Hence, the compounds of zinc are colorless. It is thus important for a metal or its ion to possess unpaired electrons in order to form colored compounds. Let us now understand the significance of empty d orbitals in the perception of color. When solid copper sulfate is dissolved in water, it dissociates into cupric and sulfate ions. The 3d sublevel in cupric ion has 9 electrons arranged in 5 degenerate orbitals, that is, orbitals having equal energy. The ligands that are water molecules approach the copper ions and form 6 coordinate bonds. Thus, hexa aqua copper 2 ions are formed. This bonding splits the 3d orbitals into two different sets of sublevels in which 2 occupy a higher energy level than the other 3. The magnitude of the splitting of the 3d orbitals depends on the oxidation state of the metal and the nature of the ligands. When light passes through a solution of these ions, some of the light energy is utilized to excite an electron from a lower energy level to a higher energy level. This amount of energy required to excite an electron corresponds to the energy associated with a particular wavelength of light. In the case of hexa aqua copper 2 ions, this energy corresponds to the wavelength of 605 nanometers of the visible spectrum, which corresponds to red light. This means the light coming from the other side will have all the colors of the spectrum except red. The mixture of the wavelengths of all the colors appears greenish blue to our eyes, and it is the complementary color of red. Hence, copper sulfate appears greenish blue to our eyes. Although we have to keep in mind here that this mixing of wavelengths is not the same as mixing paints or pigments of the same color. To summarize, we can say that the color of a metal-ion complex depends on the presence or availability of empty d orbitals in it. Bonding with ligands leads to splitting of d orbitals having unequal energy. Absorption of energy from light excites the electrons from lower energy sublevels to higher energy levels. The amount of energy absorbed corresponds to a particular wavelength of light in the visible spectrum. A wavelength of color complementary to the absorbed wavelength is transmitted, and our eyes perceive that specific complementary color. Compounds of transition elements have a hand in every pie. They oxidize and they can catalyze. We will learn about some really important compounds and their roles in various redox and